All right, so we're going to start with a very simple example of how things go wrong without the use of atomics and how to actually use them. So I'm going to call this project atomic sum. Once again, once this is done generating, I'm going to get rid of just about everything that CUDA does for me, because we're going to, we're going to have the whole thing written once again. And I know it might be a bit annoying that we keep recreating the whole thing, but it's good practice to remember how to do it. And I'm also going to do things a bit differently here. All right, so I'm going to wipe out just about everything that there is here, and well, let's begin. So let's have a main method. All right, so I'm going to basically do a sum, just like we did a parallel sum. I'm going to do a sum just by writing things into a single variable, and we'll see how totally wrong it gets. So if I do, let's have 128 variables, and then I get their size as well. So they're going to be int, and there we go. And then create the header array and basically initialize it from item count. There we go. Okay, so it's h at I equals I plus 1. So we're going to have values from 1 to 128. And then have the device side and CUDA malloc the device array. We're going to subsequently CUDA memcpy from to device from header size, CUDA malloc device to CUDA malloc host to device. There we go. Sorry, it's CUDA memcpy rather. Okay, so we copy this stuff over, and then we do a sum. So I'm going to have just count threads on the device side. Right, so we want to add up values from 1 to 8, and we've previously seen in the reduce example how this is done using a special algorithm. But what if you decided to just have a variable and do it that way? So we create a device variable called dsum with initial value of 0, and then we say, well, okay, here's my kernel. I'm going to do global void sum int d, and I'm going to basically say that, okay, the thread id is thread id x.x, and then I'm going to just add stuff. So I'm going to just say dsum plus equals d at tid. Now you already know that this will go wrong, because when you do this on several threads in parallel, it cannot lead to anything nice. But let's just run through it and see how it gets. So then I'll have hsum, and I CUDA memcpy from symbol. Notice the use of from symbol when you have a globally defined device variable. So it's from is going to hsum, and is going from dsum, and it's a single int, so size of int. And then I'm going to see out the sum of numbers from 1 to, let me get rid of the solution explorer. The sum of numbers from 1 to count is, and then hsum. And line, we CUDA free. Don't forget to CUDA free the device memory, return 0. There we go. All right, so the only thing that's missing is I'm going to just hash include stream, and using namespace std without the hash, obviously. All right, so this is good to go. Let's try compiling it and actually running it. We expect a rather large value, but what we're actually going to get is difficult to predict. Oh, that skipped the evaluation. Let's do a get char here. That should hopefully pulls it at a particular location. All right, so the sum of numbers from 1 to 128 is 128. And you can sort of see why that's happening, because if you think that the assignment to the h variable was kind of sequential, then, well, let me pull it up here. So if you keep adding stuff to the sum and you consider it as a read modifier write, so all the threads read the value of 0. And then they wrote, they added something to it. So thread 1, shall we say, or thread 0 added a 1, thread 128 added a 127, and so on. And the last thread kind of won the race, effectively. Or maybe the first thread won the race in that it wrote first, but then the last thread kind of overrode it. So we know that the sum of numbers from 1 to 8 is obviously not 1 to 8. So how would we deal with it using atomics? Well, here is where the manipulations, shall we say, start. As I mentioned previously, you do need a few extra things. And let me actually show you in the Solution Explorer. If we open up external dependencies here, where are those? Yeah, here we go. So we have different atomic function headers, and you can reference one of them, and they all contain different functionality depending on the shader model. So it's not the CUDA architecture, it's rather the GPU device architecture which is influencing what you actually get. So I'm going to go with predefined parameters here. So SM20 atomic functions. So I've got the header. I can actually kind of go and look at, scroll past all of this, look at what kind of stuff they have. And the only thing they have actually is atomic add. But that's good enough. That's basically an addition operation which lets you add the value to a particular variable, but to do it in a thread-safe way, which happens to be exactly what we need. So we can now cross this out, because that's obviously not the right way to go, and we can do it this way. Atomic add to dsum the value at TID. There we go. All right, much better, except that, yeah, this is not an error. This is just Visual Studio being wrong again. All right, so as I said, this isn't the only thing we need to modify. Another thing is the project setting. So let's go there. All right, so if we go into CUDA C++ and then go into device, then we already have some predefined code generation parameters for us, but they're not high enough to let us use atomics. We need 1.2 in both of these. All right, so let's press OK, and let's now run the thing again. All right, and now we actually get the correct value. So that's how simple atomics really are. It's just a single invocation.